All right, welcome, welcome, welcome. Today we'll be talking about leveraging determinism, or in more words, trusting deterministic execution to simplify, scale, and stabilize system. I flipped those all around. So before I talk about myself, talk about two things I like y'all to get out of this. If in your system you've got some logic that is super, super important and you're confident in, or it's something that is important to your business, make it deterministic. We'll talk about how that can help. And then if you've already got deterministic logic, don't be afraid to trust it and replay it anywhere on your stack for efficiency and profit. So just for some context, let's talk about us and our problems. Yeah, so again, I'm Frank. I'm a director of engineering at Coinbase, focusing on exchange platforms, so trading. So Coinbase is a company for where customers can do things with cryptocurrencies, one of them being trading. And so we run exchanges. Let me get a quick show of hands to see how much I should explain. How many folks know what an exchange is? Right on, right on. Okay, cool. So yeah, we, fundamentally our job is we tell people the price of a thing in the market, and we also give fair prices to people who want to trade things, right? So sort of that's what an exchange should do. It's also a fair third party between two people who want to trade some given thing, right? So the first thing that you want to think about with an exchange is that it's financial infrastructure, meaning that the exchange doesn't really make that much revenue from the massive amounts of funds that are going over the system. My experience is actually in sort of traditional markets, and in a previous life, right, folks would trade millions and billions of dollars worth of things on our system, and maybe we would make about 0.00001% on the amount of money that comes over our system, give or take a zero. So what that means is, when I think of exchanges, I think of scary explosions that are possible. So exchanges are a place where people place a lot of trust in them. And for us, an explosion on the exchange, because of how fast things are going, could not only jeopardize our own business, but could jeopardize the financial welfare of all of the folks who participate with us. So, when folks trust us with trading activity, we need to absolutely be correct. The other thing that exchanges should be for great service is that we should be very, very consistent. After all, we're infrastructure, and so you don't want people to be surprised by how long something takes, how the market behaves when you go ahead and you want to buy something or sell something. We've got to really make sure that we get back to folks about the same amount of time, because markets are constantly going up and down and up and down. If somehow you could abuse the fact that, abuse latencies or whatnot, you can effectively print money out of everyone else who is participating in the market. So for us, specifically for our exchange over at Coinbase, we want to keep our P99s under a millisecond. So when somebody sends us a message, we want to confirm, acknowledge, or reject, or express what happened back to them in under a millisecond. The other thing exchanges have to do, being these big financial institutions that are regulated by a bunch of entities, is we need to remember everything. So all of the transactions that happen over the system need to be audited, and this is like a massive volume of data. So we might have to keep like billions of dollars or millions of trades for I think in some jurisdictions, like up to like 7 years. It's just an insane amount of data. And we need to keep that to do like inspection to see if someone was like kind of doing something weird, or if a debugger like me wants to go on and actually try to figure out what someone might be doing on the exchange at any point in time. So if, right, we've got to be completely correct. We have like 0 tolerance for functional bugs, sort of because everything happens so quickly on an exchange, and you can get runaway cases really quickly. You can't really reconcile it. And our customers might notice immediately if our latencies just go up just a tiny amount. How do we like change anything? It's like terrifying, right? What we try to do to like continue to live and grow another day is try to keep things simple, right? You've got to remove as many sort of things that you need to consider when developing your service, right? So what that means, right, instead of having, right, just a swath of things that can maybe fail partially or whatnot, and you have to do sort of distributed tracing, right, we keep the vast majority of our mission critical logic, right, in one well-tested system, right? So it's very much a monolith, right? So what does that mean for us? Well, what's also not simple, right, is you can have non-determinism when you have a bunch of services, and then you basically have to, handle the cross product of the program counter of everything that's ever running, right? So please agree that that is not simple, but if you can make your system deterministic, that's simple, right? Like, hopefully that's intuitive. If you can do that, you can do some fun things. So how do you make a system like deterministic, right? Like, you can use sort of a finite state machine, right? Like you can sort of model your big program as a finite state machine where like the individual register, like all the values of all your variables, plus the program counter going through your program is basically a finite state machine, right? I stole this slide from a talk that Martin Thompson gave at some DDD Europe some years ago, but it's kind of nice. It's sort of like this like kind of academic-y thing, but we'll go from there. So given some state, right, it takes some input, and then you might have some new state, right? Instead of input, I'll say requests, but actually let me get another show of hands. Who's familiar with like sort of event sourcing, command query? Okay, so not as many, which is, I think requests are better than commands, so we'll use requests. Think of requests like an API call, some requests into your HTTP system, right? So a request, interacts with the existing state of your system and makes new state. Requests also interact with your system and might create events, like the impact of a given request, right? So we'll probably use a lot of those interchangeably, but I'll try to use requests and events rather than commands, so hopefully I remember. But what's really cool about, if your system is deterministic, right? If I order all of my API calls, right, and then apply deterministic execution, I should end up in exactly the same state and have exactly the same number of events that pop out, right? Hopefully that makes sense. So sequence requests, right, plus determinism, to save a few syllables, right, is going to basically get you can replicate it, right? You can have replicated state in events. And so, replicated state machines, right, sort of is a nice little, kind of harkens to another thing. Another show of hands, how many folks are familiar with consensus algorithms, Raft? Okay, great, get to talk about that, that's wonderful. Okay, so what are the benefits of having a nice little deterministic system? Well, for us, right, we're mostly just worried about the exchange blowing up, right? And mostly, So correctness and availability is like the most important thing on our minds. And so one nice thing you can do with determinism is you can really insulate yourself from failures in hardware. So let's talk about, let's talk about it without Raft. Let's say you've got some service, right, and it's got like a disk that's storing what happened on the system, right, and then for some weird reason it crashes, you lose it. Now you're kind of sad, right? Like, what happened to the data? Did I have good backups? What is my reconciliation going to look like? It's like quite painful, right? Well, with Raft, right, you don't handle an API request until the API request itself and basically the parameters of it are replicated to most of a cluster. So if you run, say, like a 3-node cluster, let's make sure at least 2 out of the 3 have the data. And if you're like really scared, maybe you do 5, right? So if I copy that data to multiple machines and they're all deterministic, I should be able to just run multiple instances of my same service and get exactly the same data in all these blue boxes, right? So then something kind of bad happens to the leader, right? I can fail over and basically not have lost any data or acknowledged any data that I received, right? Because I'm not handling the request until until it's replicated. So this is a lot better. You don't end up being responsible for that $1 million order that you lost, which is great. And now you get to go debug whatever that failure is, right? Hardware, restart, or whatnot. So that's one huge nice thing about determinism is that you can just like replicate your program and have like extra shields from bad things. So exchanges are latency sensitive, and there's a lot of really great consensus implementations out there. But there was never something that was like super fast. So luckily, right around when we started building this, some nice open source fast Raft implementation showed up. So we use that. And one thing that's cool about it is if your system is deterministic, you can run the whole thing on one thread, and it'll be way faster than somebody's multi-threaded implementation. If what you can do is you can basically like pin that thread to the CPU and have basically minimal jitter because you're now no longer worried about the operating system coming in, context switching out your program. And so again, you can start thinking less about all the other things, one set of things that can go wrong regarding your performance. The other nice thing that you get is, well, system is deterministic, right? So I hope it's intuitive that testing would be super, super straightforward, right? You can, if you have your sequence log of API requests, you can go back and like test, you can create test cases out of what happened on production pretty easily. You can do a lot of great things, right? And one fancy thing is that you can like troubleshoot. You have like some superpowers when troubleshooting. So again, let's say I've got my service. It's super deterministic and happy, and like some like weird behavior starts happening on it, right? Well, now I'm kind of worried, right? There's like some bug, I gotta go investigate, I gotta look at the logs, right? Like what's going on? Well, let's say if I'm running the thing deterministically and I've got access to the log, when the weird behavior shows up, right? I can go and take that log, copy it somewhere, right, like my laptop, and rerun it on my laptop. And if I've got a deterministic system, the same bug will show up, right? And what I can then do with that execution is run the thing in a debugger. So I know exactly what the state of all my registers and so that you can generally catch like sort of domain logic bugs that way, like complicated data structure bugs, right? And so I use my debugger, I figure out the problem, right? And now the question's gone, but I still got to go like fix the bug and like do something in production. So this is really cool. I can talk about this now because we sort of recently shipped it. Was you can actually take production, right? You can stream that log to basically a mirrored environment, right? And then go run experiments on it. Exact same data. It's basically like sort of exactly what production load is. And you can like see what happens if you go ahead and like try some weird configuration improvement. So this sort of mirrored sort of shadow stack thing that we've got gives us the ability to do a little bit of pre-production testing on like infrastructure config changes, which is something that like we've always had trouble testing in a functional manner, right? So being able to like mirror not only a given state at any one time, but the state as it updates live is incredibly powerful. So yeah, this is great. Like, sign us up. The thing should work. It should be fast, right? So yeah, we went ahead and built this. So the blue boxes, right, are service. That's like all of the interesting logic, right? All these, it's a monolith. So I'm saying it's a monolith in terms of logic, right? Because all the interesting logic occurs inside that blue box, and then you have some ways to access it from the internet or some local users who have some co-located machines, right? So that's in green. All the logic is happening in blue, and then for things like BI, auditability, kind of like analytics, right? We go ahead and like store all the events, send all the events that come out, store them in the cloud, right? And we've got persistence, RDS, and all this great stuff over there. So cool. Let's go through an example, right? Like, so let's say Alice wants to go ahead and buy 2 Bitcoin for 20,000 bucks. That request in blue is going to come into our gateway, get sent to the leader, right? You pick one of your cluster members to be a leader, and then the leader will send that request to both of the followers in the cluster, and then it won't start handling that order request until one of the followers confirms that it got the data. So it'll go ahead and do that. Now, let's say at this point, Alice succeeds in buying some Bitcoin, right? But what if she goes ahead and buys it from a bunch of people? So what we are going to go ahead and do is we're going to take the request, right, and then send out not the request she sent us, but like the event that had happened, right? Like, hey, Alice wants to buy 2 Bitcoin, everybody, for 20,000 bucks, right? Like, so we go ahead and broadcast that message to everyone else in the market, right? So then saying that, hey, the price of Bitcoin is $20,000 if you want to sell it. So we also replicate it across the wire over, long connection to some AWS region, right? And then like persisted in a database. And so non-latency sensitive folks can like query with RESTful calls or whatnot. So requests in this thing are in blue, right? And then events are sort of in red, right? So this arrow in the middle is kind of like big. It's like a big red arrow. And that's one thing we kind of found out when running, as a starving startup, trying to just provide sustainable value for everybody. That blue is basically 5 bits of data, right? It's like Alice, buy 2 bit, whatever. But like, let's say she does successfully buy it, meaning that there are other people who want to sell Bitcoin, right? That have already submitted their orders into the system. So Alice is going to successfully buy 2 Bitcoin, right? Well, what if she buys them from like 2 people? So when Alice goes ahead and buys 2 Bitcoin, right? Let's say she bought 1 from Bob and 1 from Charlie. So what'll happen here is we've got to tell Alice that her order was accepted, right? We got to tell Alice she got 1 from Bob. Well, we don't tell her she got it from Bob. Well, we tell her she got 1. Then we got to tell Bob he sold 1. Then we got to tell Alice that she got another 1, and we got to tell Charlie that she sold 1. So the blue box, right, 5 bits of data became this mouthful of events that came out, right? And so what we were kind of noticing is that our compute price is reasonably cheap, right? Like we sort of knew, AWS, you provision your cloud compute, and that's some value. That's not that expensive. What they really get you is network egress. So this was like fairly expensive. We realized that like the bulk of our cost was actually sending data in between our regions, right? So, okay, what do we do here? Right, we're a starving startup, we want to save some money. Can we optimize? Well, okay. How can we use the fact, what was the problem, right? Like, so kind of the crux of the issue is in general, and this is probably true even for non-latency sensitive stuff, is that your like business logic that you're coding up is like often like fast and cheap as long as it's in memory, right? The logic that you're running, the if statements, even some of the hash map lookups, right? Sort of fairly fast and cheap. But it's writing and reading data that is possibly slow and expensive, right? So, how can the fact that our system is deterministic help here, right? Like, well, let's say, Alice goes buys 2 Bitcoin. It'd be really, really great if instead of lighting money on fire, we just sent 5 bits of data over instead, and we only sent that little box over, and that'd be really great. That would cut our network costs down by some around 5, 6x or whatever, right? That'd be really great. But, well, how do you transform blue into red? Well, if your system is deterministic, it's just a finite state machine that takes Alice's order, then why don't I just rerun the thing and then send the data to Postgres or whatever thing is running the SQL or whatever the thing is sending out over the cloud. Let's send those events over IPC, right? So effectively then there's very limited network costs to all the events happening in your system. So we went ahead and implemented this, and it was super great, saved a bunch of network costs. But it also, had some other things that we kind of realized a little later that makes it sort of appealing. Why does this actually help, right? Well, so instead of sending events everywhere, we actually, and doing all this and like money on fire, right? We're just sending these small bits of data over, right? So that's great. Why does this work? Well, and you can take this to the extreme, right? You could why do I need red stuff on this side? I could just replicate my request and send it out over there on my local region too, right? You could do all this and go nuts, right? Well, this works, right? And actually improves our stuff because we found that in general, it seems like inputs are often smaller than outputs, right? And why is that the case? Well, you can sort of think of it like when you receive an API request, right? Your backend system is sort of contextualizing it with the state of its own system, and what comes out is sort of both the new data coming in and the data you've got, right? So if you weren't adding anything to the input, your system is, I guess you're just a message passer, which that's true, but a lot of logic tends to decorate and make things more interesting, right? That's how you provide value. So yeah, inputs are just generally smaller than outputs. One thing else we kind of noticed is that inputs are more consistent than outputs. What does that mean? Well, we all think about 99 percentile latency these days, right? That's pretty standard. But one thing that came up is what is your 99th percentile of network load from given requests coming in, right? So here's an example. What if instead of just wanting to buy 2 Bitcoin, Alice is I'm going to sell 1,000 of them, right? And let's say we've got 1,000 people over here ready to buy her Bitcoin. Well, what's going to happen is that one message, it's 100 bytes or something, it's going to result in a massive amount of events coming through the system and a bunch of saturation, right? An example for, say, a web system is how many folks are familiar with the Postgres write-ahead log or just general database write-ahead logs? Okay. So a database, so Postgres, one of the big web databases, and a lot of them, right, will have the state of your tables in a file somewhere, but also when the way a lot of replication schemes work is they actually send a list of all the changes to the rows as you make a SQL statement that changes it. So like insert one row creates kind of one tuple in your write-ahead log that comes out. But like let's imagine if you have like, I don't know, 1,000 accounts, and then you submit one simple SQL statement like update account set blah, 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 and you forget your where clause. Right? Like what'll happen is you will get 1,000 write-ahead log entries, and your replication pipeline is going to explode, right? Burst at least, right? And if you're an event sourcing, you've got an event sourcing system, right? And you kind of positive feedback where you're handling a lot of these events and you're putting them back into your event stream. Like that's how you kind of get thundering herd and bring down your like massively provisioned cloud system with like tons and tons of compute, because one burst can just fill all your buffers. So why is it that I say that input is more consistent? Well, I can validate input, right? If it's like bad, I can reject it, not have it go through the system, right? But I can also, right, do rate limiting. I can also make sure that people aren't sending a bunch of stuff over to fill up my command log. So it is really difficult to do that with like things that happen. You don't like some result of executing your program, it's not so easy to reject that. So that's sort of why you know kind of what the max amount of your input is, right? It's the summation of your rate throttles, right? But output, it's kind of hard. So yeah, you can protect from sort of this like bursty behavior and get really consistent sort of network utilization by not sending bursts of events that happen due to what your customer does. Another thing, right? So in summary, right, like that's how we basically make use of deterministic execution, right, which takes a sequence of logs, and we just like rerun it in different places to way cut down on data transfer, helps us sort of scale, but it also stabilizes by making it so that we have very minimal jitter in terms of network load, and results in less production incidents. Another cool thing that you can do, right, is that, so what we're doing now is with deterministic execution and rerunning it, we're effectively replicating compute, right? So replicating compute can also like simplify some of your downstream code. Just a disclaimer though, right? Like, we're not offering our firstborn up at the altar of dry, right? Deduplication is just an optimization. It's not architecture, right? But it's like fun. So let's take a look, right? So what if we go ahead and add a new color? It's purple, because a request comes in, like a read request comes in, and it needs to be synchronous, because Alice wants to know what her active open orders are, right? And so blue comes in, red comes out, it's purple, right? So this is like an RPC, or just a simple RESTful GET call, right? And you can imagine, right, that we could, for edge for if you've got folks all around the world, right, they can maybe send their read requests from all over the place, right? What you might do, right, to limit the cross-region traffic is you maybe cache, cache like geographically locally some of your state, so you can serve that information. But how is that state populated, right? You've got to like send all that. I should have made that arrow fatter, but you got to send all the events over, right? Or instead of sending all the events over, you maybe have it be kind of a lazy request to the source of truth, right? And then you cache for later updates. One thing that we can do here, right, is we want to segregate the impact of read traffic from write traffic. So we really want our head writer to just continue being able to write and not really have to serve a bunch of stuff. So great, we've got deterministic execution. My little blue boxes have all of the state of the main blue box writer, and I can basically do the query over to my locally running version and send the response over via either IPC or just like run it inside the same VM or whatnot, right inside the same process. And now you basically get, I think folks call it like command query responsibility segregation, but in general we just call it like separate the effect of writes and reads on your system. So this will scale a lot better than having a bunch of synchronous reads slow down your writes. Well, now you don't need a cache, so that saves a box. But what if like So this is kind of cool, right? Like, you know, if I took this all to the extreme, right? Like, I replicate compute everywhere. I'm just only sending these small requests all around, and I can still respond with red state, purple state, or whatever, right? It's all great. But, you know, I claim here that it's not one trick that you've done, but you've actually unlocked an entire spectrum of like cute little optimizations you can do with your topology, right? Like, you know, what if we just keep adding more services and I don't know, like just a bunch of business logic, right? Well, like maybe now we need a cache because I don't want to run another instance of our FSM again, right? Like let's say there's a ton of those. But, well, if instead of a cache, it's like just another instance of the system and go ahead and replicate, right, all the state from, you know, my replicator is like some message bus, like you could use Kafka, you could use something faster, right? And then that thing can go ahead and serve. But I'm hoping that this kind of highlights that you don't have to go to the extremes with replicating compute or replicating data. You can kind of mix and match depending on your own system characteristics, right? So yeah. Running in this way, what are some of things that we need to kind of worry about? Well, it's kind of like an FAQ. The first thing we need to worry about is this is really only useful if you are very confident in the logic that you are replicating, right? It's best for things that you really need high performance out of your system on, or mostly super mission critical. You don't want anything to go wrong with it. So presumably this stuff is well tested, right? And if it's not, well then you've just replicated a bunch of bugs everywhere too, right? The other thing about trying to run a deterministic system is that the system should be deterministic. None of those boxes can do anything different given the same sequence of requests, right? Because otherwise, like, it's pretty horrible. It's like you've broken TCP, right? Like, what would happen if, you know, in your little set of services, like TCP was suddenly broken, you couldn't trust anything, right? So what that means is, when you deploy code and you have different versions of your FSM running, right, your finite state machine, your replicated state machine, you have to do the old thing when replaying inputs from the old times, right? So your new code must do the old thing. So, well, how do you solve that? How do you actually change your system? We basically send a message, send an API request into our input log to actually change things after we've deployed code. So this is like pretty powerful. Effectively, what you want to do is decouple code deploy from behavior change in your system. Once you do that, right, you can deploy whenever you want, as long as you can maintain, you know, minimize like the switchover costs or failover costs when you eventually bring down your leader, right? So after we have all this, right, we can now run 24/7. And I mean, I don't know, everyone, raise your hands if you run a 24/7 system. Okay, so it's like pretty easy, like 24/7, like y'all have been solving it for a long time, but in traditional markets, like none of them are 24/7. So, but with this approach, even that can be 24/7 now. So, woohoo. Well, if you need randomness, the random output should be deterministic. So you need to use a seed for that stuff, or else you'll get drift. Finally, when you're doing work and you're single-threaded, right? If you start something that does a bunch of work and it locks up, you know, is like, say, for example, infinite looping or something, you've effectively caused an outage because you can't do anything while you're doing work. Right? So that's the extreme example. But let's say you're not infinitely looping. Let's say you're doing, I don't know, like 100K, 1 million items of transactions spawned off by one request, right? To get less jitter in your response times, you may want to like make some trade-offs in dividing that work into stages, right? Another thing about scaling is that, at least for us, it's really, really easy if everything fits in memory, then it can run on your laptop and stuff. right? So that sounds kind of scary, but a lot of stuff can fit in memory. So what we do, because we care about performance, is we generally eschew kind of variable length data and like arbitrarily nested stuff. So basically, instead of having things kind of be document stores and just like nested objects instead of strings, all of our data, which is branching on our logic, is fixed length. So a lot of kind of using registers, right, 64-bit integers, 34-bit integers, 32-bit integers, and instead of processing like massive arrays of things, we try to process them one transaction at a time. So if that's the case with a few gigabytes of RAM, 64-bit integer is about 8 bytes, right? You can fit like millions of customers' stuff in memory on like one machine, right? So you don't really need to shard if you're careful about how you model how your data fits. Also, well, you'd scale better if you could use multiple threads. Well, I submit that having one thread, a hot thread running at, I don't know, like 3-point-something gigahertz or whatever, you can basically have programs that can handle complicated business logic in the low digits of micros on the cloud, and maybe in bare metal you can even go less than a micro. A microsecond, right? So what that means is your throughput is like 700K per second up to maybe about 1 million, right, per second. Should be generally plenty for, a lot of systems, right, that you can do all on one box of logic, maybe replicated 5 times, but instead of having, say, like hundreds of machines running your logic, right, and a gigantic database. So it's a lot cheaper. One thing you do have to worry about is you do have to apply a little bit of craft because your thing is single-threaded, which means, again, it's all handling, it can only handle one thing at a time for simplicity, right? But that means you don't want to do a lot of complicated stuff. You want to make sure that you keep your 99s and 99.9s down to maintain the SLOs you like. But if you've got a lot of control over your system, you can do that. And finally, you have to rate limit your inputs, right? Because a client that has a runaway case could just fill your logs with junk, right? And now you're over here replicating junk, and that's generally not good for availability. So it's like really, really important to validate your input, which in general we do, right? So yeah. In conclusion, what we say generally is that like simplicity, right? Keeping things simple, removing lots of other concerns, right? Generally gets you stability, right? Should get you performance, and get you development speed because it'll, more logic, more domain logic can fit in your head, right? And how do we get simplicity, right? Hopefully I don't have to sell simplicity, right? Everyone wants to keep it simple. But, if you've got like important logic, right, making it deterministic keeps it simple, right? And then once you have that, you can do, some fun things to save money and scale up, right? So yeah, and if y'all already do this, then really, really happy to discuss stuff. Thanks, everyone.